Hi guys, today I'd like to talk to you about Fourier transform. Uh, Fourier transform. Actually, it will be okay. I won't be so technical to differentiate between Fourier transform and Fourier series. Although maybe I will get to the end and say what's the difference between the two. But basically, the idea is to give sense on to expression like this. So where you have a function, whatever function you want, and I will give some specification for the function that you can put there depending on the application. And then you sum from minus infinity to infinity of some coefficient, and yes, and these are, and there is an I here. Okay, good. So what this means is, so suppose, so first things, let's try to break it in pieces. As you can see, this this expression is a sum, an infinite sum, but we know what an infinite sum is because we know what a limit is. We take big N to the infinity, and then we sum from minus big N to big N of the same coefficient. And we take the limit of this expression here on the left, sorry, on the right. So this expression here is a sum, s to the n, which is basically a sum of coefficient, which are numbers, and complex values. Okay, we know what a complex value is. Um, and so on. So we start from minus n, and we go up to a to the n, e to the x, n, bn, and all the bits in between. Of course, this is each of these s of n is a finite sum. So finite sum, we exactly know what to do. We just sum bit by bit. We know how to sum complex numbers because if we have a e to the I x and we sum it to b to e to the I y, for example, these are just two elements of one of these sum. Let's break it into pieces. We have a cosinus of x plus I a sinus of x. I'm just using the definition of e to the ix that we know of, which is cosinus of x plus I sinus of x. Okay, plus b cosinus of y plus I b sinus of y. Sorry, y. Said y and I wrote x. Nice. And then we just group the element here with the same real part, which are the cosinus. Okay, and then we sum the complex element, which in this case is the sinus part inside. Okay, not saying that anytime it's easy to do the sum, but it will be another complex number, which will have a real part of z plus I imaginary part of z. Okay, so nothing complicated here. This sum has many elements. You keep doing this summation and you end up with a complex number which depends on n. And then you have a list of these complex numbers. So we have, so let me erase these bits. So we know how to sum complex numbers. We're not afraid of that. We know how to sum finitely many numbers. Okay. So again, not an issue there. It's maybe boring, but you can do it on a PC if you like. So nothing fancy there. So in the end, we have all those Sn in the end are complex number Zn, and we have Z0, Z1, Z2, Z3, Zn up to Zn. Actually, we said we start from minus. That's important because I will tell you in a why. In a second why. Z of minus n, Z of 0, Z of, and we have a list of these numbers, okay? And our function will be related to the list of this number. But how? Related to how? So we need to take the limit of this sum. So this Z number will draw some points in a circumference. This is the complex plane, and each of these will jump from one place to another for each of this n. Okay, we don't know where they end up, but if there is a limit, at some point all the complex number will bunch around a particular number, which is exactly the limit of Sn for n goes to infinity, which is a complex number, precise complex number, and this is for each x. So actually you can think about this as depending on x. So you choose an x, and as you can see the x's are changing here. Sorry, and this is not changing, this is like so and like so. Sorry about that, I was putting too many emphasis on the yes. So what I'm saying is that yes, so basically at this point you have many limits for each of x, so you have a new function which is hopefully related to the original function, which is f of x. The magic of this is that you can pick pretty much any function that you can think of. I will give some more details because it's not technically true that you can take any function, of course, but I mean you can take the function and of course do this procedure and get some numbers. The important thing is that sometimes you want to go back from this number to the original function, and that's not always guaranteed. But let's go step by step. So at the moment we're just playing with these complex numbers, and you might say, okay, it looks complicated. Why would I do that? Okay, so maybe I will link some historical facts about Fourier transform because it's fascinating how they find out, if you believe what's written in the history. Apparently it was discovered to help solving some diffusion equation of heat transfers. So when you heat something, for example a rod of metal, you have a hot spot with high temperature, and then with time you will see that this hot spot will spread around the rod, right? So you have a heat spot. That so I will draw you just a schematic. So you have a piece of metal, you have a heat spot, the temperature is very, very high. I don't know, 20 degrees, I don't know, Celsius, whatever, very, very high. Let's say 200. Okay, 200. And then with time, this rod will let's say thermalize. So the temperature will spread and eventually will spread and cool, because of course on average, so the energy is conserved, but on average in each point of the rod you will have a little bit less of energy, and if there is nothing, if it's in vacuum, the total energy will be of course conserved, otherwise you get some dissipation in the environment. But the cool thing is that in the end you have a very nice homogeneously heated metal rod, for example, with a temperature which is fixed, which is less than the one that you started from. Okay, so the cool thing is that the equation that goes from here to here can be easily solved, well, not easily, but can be solved effectively using this trick of the Fourier transform. And I will give you, and I hope I will give you an example of this, why this trick works, which is very powerful. Okay, so enough with this intro. Let's start to do. No, I want to give you a couple of others ideas. So nowadays, I mean, to be honest, since the birth of Fourier transform, it was clear that the power of this tool to describe physics phenomena, especially for periodic, but also non-periodic, I will tell you why, periodic functions. So if you think about a periodic function is, we saw already some, let's pick in the real plane. So let's forget about complex number for a sec. A periodic function is a function that gets periodic, meaning that has the same values repeated over and over again after a certain, what is called period. Okay, so the distance between the value with the same and with the point with the same value is called period. And as you can see, the period is the same between this point and this point. So basically you have an original shape, which I will highlight with these dots, which is non-periodic. This is, as you can see, it's this bit here, you cannot find a period here, okay? And then you shift it solidly by the period, the distance of the period, and you stitch it next to each other many times. So no, I'm not very technical here. Sorry, stitching is not mathematical or physical term, but it works. So you literally do this over and over again. Okay, nice. So this is periodic. We know already quite a few, to be honest, periodic functions, because we studied, or at least we encountered, maybe not studied too much, but we encountered the sinus of x and its relative cousin cosinus of x. We know them because of the exponential, but we know them from the vectors matrix videos as well. When you have a vector, you have two components, sinus of x, cosinus of x, and sinus of x, and so on. And those are periodic. Of course, well, it's not okay. We need to prove that, but I'm not going to do that. But combination of periodic function can be periodic. I'm not sure if it's definitely that it is periodic. I think it is, but let's not go into the details. Definitely the sum, if you do the sum or the product of periodic function, okay, or the product of periodic function, this will be periodic as well. Okay, because we know why. Because we have trigonometric expression like this, which, as you can see, relates a periodic function with sum of products of periodic functions. So if the one on the side here is periodic, which it is because we know that it is, it means that also the sum and the products of um, trigonometric function like sinus and cosinus is periodic. Okay, this should convince you enough that we are on the good side. Okay, so now let's do a very easy Fourier transform. Okay, let's do a very easy Fourier transform, and then oh, sorry, why I wanted to say periodic function, because basically what happens is that when you do the Fourier transform, and if you see this this expression here, you can write it as a sum. Let's say, let's keep it from minus infinity to infinity of a of n, and then you can explicitly break the sinus and the cosinus, and again I mix them up. I don't know why I keep mixing them up, but it's easy to remember there is a cosinus first because e to the 0 is 1 and the cosinus is 0 and 1 and the sinus is 0. So that's an easy trick to remember it, but I always mix them up. Sinus of x of Pn. Okay. And as you can see, you already can understand where this is going. So definitely, but not definitely, let's say, you can be convinced that if f of x, suppose f of x is periodic, then we can think, well, we can kind of understand why this summation is working, right? Because it's basically a sum of periodic components. So if f of x is periodic, maybe, I mean, it's a big deal when they discovered it, so it's not, I'm not saying that it's easy, but I'm just saying that once you see the functions, you can kind of say, okay, yes, I mean, this is periodic, the sum of the two will be periodic. And then there are the intricacies of the limiting factor, which is the nasty bit. But if you truncate the sum as we usually do for a large n and neglect the very, very final part of the limit, you can kind of see that these things works. So if f is periodic, then this decomposition makes sense. Okay, but let's see this decomposition in action. And I want to do a very simple example, which is maybe not very enlightening, but, and I hope I'm not, well, let's do, and I always, let's do the cosinus. Okay, I mean, the cosinus is easy because you say, no, let's do the cosinus. Let's see if I can do the cosinus. Cosinus of x. Of course, you see there is this an and an here, so we cannot set one 0 and the other not 0. They need to be both present. Okay, so one easy thing to see is that the cosinus can be written as cosinus of x plus I sinus of x plus cosinus of x minus I sinus of x. And actually this is 2 times the cosinus. Let me show you why this is true. It's a trick, but it's a very important relation. So these two things cancels out. I just add and remove the same value, and then add it twice the same value cosinus here. So we have 2 cosinus plus 0. But why I'm writing like this? Because now we can see that cosinus plus I sinus x is e to the ix, and cosinus minus I sin to the x is plus e to the minus ix. Okay? Let me write it better here with a little space. So this is, we understand that this is a minus, and this is an I minus ix. Okay. And then there is a 2 here. Okay, so long story short, we can see that this has the shape of a Fourier transform. A very, very, very easy Fourier transform because it's made out of only 2 components. So the sum is super easy. It's 1 over 2 e to the ix plus 1 over 2 e to the minus ix, which basically is just two components, and 1 and minus 1, and the component with an equal to 0 is 0. Okay, so this sum already works with the cosinus, of course, but this is this is not, just to show that it's not super, it's not completely out of the blue, basically. Okay, now if you do this game over and over again, suppose you want to sum another cosinus, and then you 3x, okay, and then you do the math, and well, I'm not doing it now. Oh, maybe yes. Okay. No, I'm not doing it now, but you can construct the sum of the sum of these components. Maybe 2x I can do. And maybe 2x I can guess it from here. 2x, okay, is cosinus of x plus x, which is sinus of x cosinus of x minus sinus of x cosinus of x. It's easy to see if I mess it up, because now we know that cosinus of x is this function here, but we also know, let me write it here, then I will stop and then pause for the next video. Sinus of x, we can easily prove that e minus is the difference divided by 2i. In the same way that we derive the cosinus, we can derive the sinus of x. Now, if we plug this into these relationships into this one, we can find what cosinus of 2x looks like, and there will be many terms. Not too many, but more terms. Okay, so enough for the moment. So then we will do some interesting function and hopefully other examples. Okay, hope you enjoyed. See you later.